In this video, we are going to introduce the null space, the column space, the row spaces, and talk about how they relate to linear transformations. This is our overview slide, which we'll spend a couple of minutes talking about, and then we'll go through each of these topics in more detail with more examples. The null space of an M by N matrix, denoted null of A, is the set of solutions to the homogeneous equation AX equals 0. So in other words, it's the vectors that get mapped to the 0 vector by the transformation A. We have this theorem here that says the null space is a vector space. Next, we'll look at the column space of an M by N matrix denoted column of A, and that's the set of all linear combinations of the columns of A. So if A is the matrix with column vectors A1, A2 up to AN, then the column space of A is equal to the span of the column vectors A1, A2 up to AN. And we similarly have a theorem that says the column space is a vector space. Next, we have the row space of an M by N matrix denoted row A, and that's the set of all linear combinations of the row vectors. We have this other theorem that says that the row space is also a subspace, a vector space. We'll spend a little bit of time contrasting the null space to the column space, and then finally we'll look at linear transformations and define the analogous kernel and range. So kernel is the null space of a transformation T, and the range is of a T is a set of all vectors that get mapped to from T. So it's the set of all vectors T of X for some X and B. That's it for our quick overview, so we could start by looking at the null space in more detail. The null space of an M by N matrix, denoted null A, is a set of solutions to the homogeneous equation AX equals 0. So if we think of A as being something that takes a vector X and then maps it to another vector Y, which is equal to AX, then all the vectors, here I have 4 blue vectors that get mapped to the 0 vector over here. And these 4 blue vectors would then be considered the null of A. It's the things that get, crushed down to 0. So in set notation, the null of A is equal to vectors X such that X is an Rn and AX equals 0. A quick example, if A is the matrix with column vectors 1, -5, -3, 9, -2, 1, and if we want, the question is to determine if this vector U, 5, 3, -2, is in the null space of A. So what we need to do is look at A times U. So here we have A times U, and we see it's equal to 0, 0. So it does indeed get mapped to the 0 vector. So yes, this U vector is in the null space since AU is equal to 0. Now we have the theorem that the null space is a vector space. So the null space of an M by N matrix A is a subspace of Rn. Equivalently, the set of all solutions to the system AX equals 0 if M homogeneous linear equations and N unknowns is a subspace of Rn. And we're going to prove this, and we have this hint that the null of A is a subset of Rn. Before we do the proof of the video, I do want to back up and just make sure that we remember that if A is an M by N matrix, then A maps vectors from Rn into vectors to Rm. So in other words, I took this from our last example. Here A is there's 2 rows, so 2 by 3 columns, so 2 by 3. So M is equal to 2, N is equal to 3. So this matrix then, we multiply it by things in R3 or Rn, and then we get something in R2 or Rm. So hopefully it's clear to you that if A is an M by N matrix, A maps from Rn to Rm. Now the next point I wanted to make is that Rn is a vector space, and that's from, the video when we talked about vector space. Remember there were 10 conditions we had to meet: closure, commutative, addition had to be commutative, associative, and then there were some other conditions on scalar multiplication. Well, Rn was our canonical vector space, our premier vector space. It's the one that we're most familiar with. So that's the second thing we want to establish. Rn is a vector space. And then last, the vectors in Rn that A maps to the 0 vector in Rm, the Rm 0 vector, that's a subset of Rn. And so this is the hint that we're going to use. The null of A is a subset of Rn. And the reason why there's this hint is because once we know it's a subset, we only have to prove 3 properties. We don't have to go through all 10 properties of the vector space, because the other 7 that we don't prove, it's inherited from Rn. So we'll start with the first, that the 0 vector of Rn is an H. And then second, that H is closed under vector addition. The null space in our case is closed under vector addition. And last, that the null space is closed under scalar multiplication. And the first statement, the 0 vector is in the null of A, is almost trivial, right? A times the 0 vector in Rn is always going to equal to 0, because A times 0, any 0, is going to be 0. The next thing we need to show is the null of A is closed under addition. So we're going to start by taking U and V in the null of A. So that means AU is equal to 0 and AV is equal to 0. And we want to consider what happens when we add U and V together. Here, so we have AU plus V. Well, by property of vector and matrix multiplication, that's going to be equal to AU and AV. But since U is in the null space, AU is equal to 0, and since V is in the null space, AV is equal to 0, and 0 plus 0 is 0, and therefore U plus V gets mapped to 0, which means it's in the null space of A. This third condition, closed under scalar multiplication, we need to show the null space is closed under scalar multiplication. So again, we're going to let U be in the null space of A, that is AU is equal to 0, and we're going to consider what happens when we multiply U by a scalar. So here we have AU, where A is a real number. Then we look at the matrix A times the scalar AU. Well, this is equal to, we can factor out our scalar, and that's just from properties of matrix and vector multiplication. So we have the scalar A times AU, but since U is in the null space, AU is equal to 0, and then the scalar A times 0 is still equal to 0, and therefore our AU is in the null space of A, and we have completed our proof. Our next example is let H be the set of all vectors in R4 whose coordinates A, B, C, and D satisfy the equations A minus 2B plus 5C equals D and C minus A equals B. Show that H is a subspace of R4. There are a couple of ways we can show this set H is a subspace. However, since we're talking about null space, I'm going to rewrite these equations so they're homogeneous. In other words, so they're equal to 0. So I have A minus 2B plus 5C minus D equals 0. And I have A minus B plus C equals 0. Now this system of equations can be represented by the matrix A times the vector A, B, C, D, and we set it equal to 0. So in other words, we want the vectors that get mapped to the null space. And in particular now, since H is the null space of this matrix A, H is a subspace of R4, because we know that the null space is a vector space and a subspace of Rn. Next example is to find the spanning set for the null space of the matrix A, where A has the column vectors -3, 1, 2, 6, -2, -4, -1, 2, 5, 1, 3, 8, -7, -1, -4. Since we are talking about the null space, we need to consider the matrix equation AX equals 0. So here I have set up the augmented matrix. I've done my row reductions here until I finally get to x3 is equal to minus 2x4 plus 2x5, and x1 is equal to 2x2 plus x4 minus 3x5. So I have x2, x4, and x5 are free. So I've rewritten my solutions for the AX equals 0 as my x1 is 2x2 plus x4 minus 3x5. My x2 is free. My x3 is negative 2x4 plus 2x5. My x4 and x5 are free. Now, I want to write this as a vector times x2, a vector times x4, and a vector times x5. In other words, using my free variables here. So my first coordinate for x2, I have the coefficient of 2. For my second coordinate, I have a coefficient of 1. There's no x2's here, so that's 0. No x2's in the fourth or fifth coordinate, so these are zeros. Looking at x4, over here I have a coefficient of 1. Here I have a coefficient of 0, negative 2, 1, and 0. Finally, for x5, here I have a coefficient of negative 3, 0, 2, 0, and 1. So this is what my solutions look like. They look like linear combinations of these three vectors, 2, 1, 0, 0, 0, 1, 0, negative 2, 1, 0, negative 3, 0, 2, 0, 1. And another way of saying this is the null of A is equal to the span of these three vectors, because span is just the same thing as linear combination. We are ready to go on our next topic, which is the column space of an M by N matrix A. We denote that with column or COL-A, and it's the set of all linear combinations of the column vectors of A. So if A has the column vectors A1, A2 up to AN, then the column space of A is equal to the span of A1, A2 up to AN. So here I've moved up my definition of the column space, and we have this theorem. The column space is a vector space. So the column space of an M by N matrix is a subspace of Rm, and we'll do the proof next. Actually, let me back up. Before we do the proof, again, let's look at this because we're saying it's a subspace of Rm. Remember, the null space was a subspace of Rn. So let's look at this again, Rm. So A, if it's M by N, then A maps from Rn to Rm, and we had this example here last time. But now the column space is the linear combinations of these the vectors. I'm just going to label them A1, A2, and A3. If it's a linear combination, you can see that it's going to be a, how many rows? 2 by 1, and a 2 by 1, and a 2 by 1. So we're going to be in R2 at the end once we add everything up. It's going to be 2 rows, 1 column. So in other words, the column space is a subspace of Rm. So that's important. It's different from the null space. To do our proof, we're going to use this theorem here that we had from a previous video about vector spaces and subspaces. And what we said is if we have a set of vectors in a vector space, then the span of those vectors is a subspace of V. So now, since the column space is the span of a set of vectors, by this theorem here, the column space is also a subspace. I have one more note that you can think of the column space as a set of vectors B such that B is equal to AX for some X in Rn. So that's another useful way of thinking about this because it relates to, solutions of AX. In other words, it's in the column space if it's a linear combination of the column vectors of A, which means it's a solution of the equation AX for some X. This next example, find a matrix A such that W equals the column space of A. So W are vectors of the form 6A minus B, A plus B, and minus 7A. So we want a matrix A such that the column space looks like this. Since I want to make W look like a column space, I want to break it down into some like vectors times different scalars. So this form of W, I want to break it apart. So what I'm going to do, much like we've done with other vectors here, I'm going to break apart my A and my B. So here I have a 6A, I have an A and a minus 7A, and I have a minus b, and a 0. So now I can make this vector into 6, 1, minus 7 times a, and minus 1, 1, 0 times b. So I have something in this kind of column space or linear combination form. And from here then, I can use these two vectors as the columns of A. And just kind of to look at this in the other direction, so this is my final answer. But just to say, what does, again, if this is A, what does the column space looks like? It looks like the linear, the span, or the linear combinations of these two column vectors. And then if I multiply this out, this would be, and actually here the variables were A and B, so let me change that. You can see that this here, the column space of A, are linear combinations of these two vectors, and when you multiply by the scalars A and B and then add them together, you get exactly W. Our next topic is row space. Now that we've done column space, it kind of makes sense. Maybe we'd want to do row space, and that's denoted row A, and it's the set of all linear combinations of the row vectors. Each row has n entries, so row A is a subspace of Rn. So I've moved my definition of row space up here just to give us more space, no pun intended. For a quick example, if we have our matrix A, which has the column vectors negative 2, 1, 3, 1, negative 5, 3, 11, 7, 8, negative 5, negative 19, negative 13, 0, 1, 7, 5, negative 17, 5, 1, 3, our row vectors then are negative 2, negative 5, 8, 0, negative 17, 1, 3, negative 5, 1, 5, 3, 1, negative 19, 7, 1, and 1, 7, negative 13, 5, negative 3. Now my row space is equal to the span of these four vectors, which are the row vectors here: 2, negative 5, 8, 0, negative 17, 1, 3, negative 5, 1, 5, 3, 11, negative 19, 7, 1, and 1, 7, negative 13, 5, negative 3. Before we go on, we're just going to take a moment to contrast the null and the column space. So we'll see in the coming chapters the null and column space are related. They are very different, however. When A is not squared, the column space and the null space exist in entirely different universes. In other words, for an M by N matrix, the column space is an M-dimensional space. Remember, it's a subset of Rm, whereas the null space is an n-dimensional space. Remember, it's a subset of Rn. For our first example, let A equal to the matrix with column vectors 2, negative 2, 3, 4, negative 5, 7, negative 2, 7, negative 8, 1, 3, and 6. The first question, if the column space of A is a subspace of Rk, what is K? The second question, if the null space of A is a subspace of Rk, what is this K? We had done something like this, or we looked at something like this in a previous example, but this is pretty important because if you don't know what space you're in, then you're kind of lost. So let's make sure you're not too lost. So here we have A, a matrix A. It has 3 rows, 4 columns. So M by N is rows, columns, 3 rows, 4 columns, 3 by 4. When you multiply this matrix times a vector, because you multiply row by column, you know that you need 4 entries in this column to be able to do your matrix multiplication. Secondly, you know when you do your matrix multiplication, you're going to multiply your first row by the column to get your first coordinate, your second row by the column to get your, or the vector to get your second coordinate, and then your third row by your vector to get your third coordinate. So in other words, you're going to have 3 coordinates, so your answer will be an R3. In other words, A maps from R4 to R3. And remember this 4, it seems kind of funny because you almost want to say it goes from 3 to 4, but it's the other way around, because remember, when you multiply a matrix times a matrix, it's these 2 inner dimensions that have to match, and these outer ones are what tell you the resulting matrix, or in this case, vector, will be. So this is your domain, this is your range. So your domain is R4, your range is R3. The generalized statement is your domain is Rn and your range is Rm. So now the null space, remember, the null spaces consist of the vector x such that ax equals 0. So there are these vectors here. So the null space are the vectors from R4. So the answer to this question is k is equal to 4. Since we used k equals 4 here, you might guess then that the column space would be 3, the other one, right? But there's an easy way to look at this. This is even easier to look at because the column space are the linear combinations of the column vectors, or the span of the column vectors. You can look at this as the first column vector times x1, second column vector times x2. But you look at this and when you add them up, you're going to get something, a vector in R3. So the column space is a subspace of R3. So k is equal to 3. Actually, that was part A, and I answered part B first. And so, again, this comment here, if A is not square, the column space and the null space exist entirely in different universes, right? This is here, the null space is a 4-dimensional object in R4, whereas the column space, that's a 3-dimensional object in R3. For an m by n matrix, the column space is the m-dimensional space, where the null space is the n-dimensional space. So this is an important point, so that you don't sound lost, that you don't sound like you don't even know what space you're in or what universe you're in. Our next example is given the matrix A with column vectors 2, -2, 3, 4, -5, 7, -2, 7, -8, 1, 3, 6. Find a non-zero vector in the column space of A and a non-zero vector in the null space of A. The column space is pretty straightforward. It's just linear combinations of the column vectors. So I'm just going to let x equal 1 and x2, x3, x4 equal 0. So I'm just going to choose 2, -2, 3. You could have chosen everything is equal to 0 except x4 is equal to 1. Or you could choose, if you wanted to do more arithmetic, you could choose x1, x2, x3, x4 all equal to 1. But whatever you choose, it's just some linear combination. The null space is a little more work. We need to consider ax equals 0, which means we need to look at the augmented matrix. Here I have the augmented matrix, which I row reduced until I got x4 equals 0, x2 is equal to x3, and x1 is equal to -9x3. So x3 is free. I wrote my solution as x1 is equal to -9x3, x2 is 5x3, I have my x3, and x4 is equal to 0. So taking out my x3, I get the vector -9, 5, 1, 0 times x3. So any scalar multiple of 9, -9, 5, 1, 0 would be in the null space. So I chose let x3 equal to 1, and this is my null space vector. In this next example, we're going to use the same matrix A that we had in our last example where we found the column space and the null space here. The first question is to determine if the vector u equals 3, -2, -1, 0 is in the null of A, and could u be in the column space of A? And second, determine if the vector v equals 3, -1, 3 is in the column space of A, and could v be in the null of A? So here's my u, which I wrote as kind of in this vector format, and v in this vector format as well. And one thing you know is like a vector, the vector u, any vector, it can't be in both the null and column space because these are different universes, remember, different dimensions. We'll start with is u in the null space of A. That's not too bad. We just multiply A times u and we look to see if it's equal to 3. But on my when I was calculating my second coordinate, I found it was equal to -3. So I just stopped there and said, no, it's not in the null space of A. Now, u is in R4, and the answer is, can it be in the column space of A? So the column space of A, because it's linear combinations of the column, is R3. So u is in R4 and cannot be in column space of A, which is R3. Our next question, determine if V is in the column space of A. So in other words, is V a linear combination of A, the vectors of A? And if it is, let's go ahead and find it. So we need the augmented matrix. Here's A and here's V. I row reduce until I get this solution here. So I have x4 is equal to 1/17, x3 is free, x2 is equal to -2 plus 5x3 plus 4x4, and x1 is equal to 1/2 3 minus 4x2 plus 2x4 minus x4. So I can figure out, I can plug in, x3 maybe equals 1, and I can find a solution. But the idea is there is a solution, and therefore V is a linear combination of the column vectors of A, which means it's in the column space of A. Now, V is in R3, right? We plug in our coefficients in front of each of these vectors, and we get V. But V here, which is given here, is in R3. But remember the null space, right? They look like R4, so V cannot be in the null space. Topic regards linear transformations. If you recall, linear transformations are exactly those transformations that can be represented by a matrix A. So a lot of these ideas are very closely related to the idea of kernel and range for linear transformation. First, let's review. A linear transformation, T, from a vector space V to a vector space W, is a rule that assigns each vector x in V a unique vector T of x. So we take x, we transform it. Usually we have a matrix A to represent that linear transformation. So we take a vector x in V, transform it to a vector in W, and it's linear if T of u plus V is equal to T of u plus T of V, and 2, T of a scalar C times u is equal to C times T of u. The idea of kernel relates to the idea of null space. So the kernel of T is a set of all u and V such that T of u is equal to 0. And here the 0 vector is the 0 vector in W. And then the range of T is a set of all vectors in W of the form T of x for some x in V. So your normal idea of range, something that gets mapped onto. The kernel and range of T are both subspaces of V. Our first example of linear transformation will be differentiation. So let V be the vector space of all real-valued functions f, defined on an interval AB, with the property that they are differentiable and their derivatives are continuous functions on AB. Then let W be the vector space C of AB of all continuous functions on AB, and let D be the differential function that goes from V, the space of all real-valued functions with derivatives, mapping to W, the set of all continuous functions. That will be the transformation that changes f in V to its derivative f prime. And in calculus, there are two simple differentiation rules, so we're not going to prove them, but they were proved in calculus. That one, df plus g, so we have two functions, then their derivative of the sum of the functions is equal to the sum of the derivative of each function. And second, the derivative of c times f, where c is a scalar, is equal to c times the derivative of f. That is, D differentiation is a linear transformation. Now we can ask, what do the kernel and the range look like? We'll start with the kernel. So the kernel, remember, those are the things that get mapped to 0. So our mapping is differentiation. So what things do the derivatives map to 0? And the things that get mapped to 0 are the set of constant functions. The constants get mapped to 0. The range, then, is also the set of all continuous functions. As long as you can take an antiderivative, then you can be in the range. This next example is from differential equations, y double prime plus omega squared y equals 0, where omega is a constant. And this equation is used to describe a variety of physical systems, such as vibrations of a weighted spring, the motions of a pendulum, and voltage of an inductance capacitance electrical circuit. The set of solutions is precisely the kernel of the linear transformation that maps the function y equals f of t into the function f double prime of t plus omega squared f of t. But finding an explicit description of this vector space is a problem for differential equations. Before we do our next example, just some background. A common technique used in stock market is technical analysis. Statistical trends gathered from stock market trading activities such as price movement and volume are analyzed. Technical analysis focuses on patterns of stock price movement, trading signals, and various other technical analytical trading tools to evaluate the security's strength or weakness. A moving average is a commonly used indicator in technical analysis because it smooths out price action by filtering out the effects of random price fluctuations. In the final example for this section, we examine the linear transformation. And just a word about moving averages before we do our example. So I have an example of a 3-day moving average. So this is day 1, 2, 3, 4, 5, 6, 7, and the prices are 2, 3, 4, 3, 2, 4, 5. So I plotted them in black. So day 1, it's 2, day 2 is 3, day 3 is 4, it comes back down to 3, then 2, then 4, and 5. If I do the moving average for 3-day moving average, I have to wait till the 3rd day before I get my first quantity, but it'll be the average of the 3 days. So that would be 6 plus 3 is 9, so the average is 3. My next window on day 4, I can take the last 3 days and take an average, and it's 3 1/3. The 3 plus 3 is 6, plus 4 is 10, divided by 3 is 3 1/3. The next day, I can take the last 3 days average. That's 6 plus 9, so the average is 3. Then the next day, I take my 3-day moving average. It's 6 plus 3 is 9, divided by 3 is 3. And my last moving average I can take is 5 plus 2 is 7, plus 4 is 11, divided by 3 is 3.6. So here I plotted my moving average with the blue. And you can see what it does is it sort of smooths out the kind of peaks and kind of, it gives you the general trend. It's going up, it's kind of stable, sort of, it's going up, but it gets rid of the small noise. And in this example, for our next example, we're going to be looking at a 2-day moving average. So our example is to let this piece of K, and this is an S, that's those doubly infinite sequences, represent the price of a stock that has been recorded daily over an extended period of time. Note that we can assume that piece of K equals 0 for K outside the time period of study, so that it can be infinite, but we don't have to have prices for an infinite time before and after the current date. So to create a 2-day moving average, the mapping M2 from S to S, from an infinite sequence to an infinite sequence, defined below over here, is applied to the data. Show that M2 is a linear transformation and find its kernel. So here's M2. We take, since it's a 2-day moving average, we take the current day and the day before and we divide by 2. So we average over the last 2 days. For it to be linear, we have to have 2 sequences. You know, they have, like, I don't know, this is stock A, this is stock B. They're 2 signals, and we want to show M2 for if we add the price. So again, the adding is, you know, day by day, we're adding them. So we have PK plus QK. So this is day K. So we have one stock and another stock. And then for the day before, we have PK minus 1, PK2 minus 1. And this should be a plus over here. So these are just real numbers now, right? These two, the P sub K, the Q sub K, and then these two, P sub K minus 1, Q sub K minus 1. So we can move them around. They're commutative. So now we're, and also associative. So we're going to get P sub K, and we're going to move P sub K minus 1 together, the Q sub K and the Q sub K minus 1 together. So then we can divide the fraction. So what we get here is P sub K and Q sub K, M of P sub K and M of Q sub K. So here we show that the addition satisfies the condition of linearity. So now we need to look at the scalar multiplication. So we have C times P sub K plus C times P sub K minus 1 over 2. So we can factor out the C because, you know, now we're thinking term by term. So we have C times P sub K plus P sub K minus 1 over 2, which is C times M2 P sub K. So we've shown that M2 is linear. So next, on the next slide, we'll show what the kernel looks like. So first, P sub K is in the kernel if m2 of p sub k is equal to 0, and we know m2 is equal to p sub k plus p sub k minus 1 over 2. So in other words, p sub k has to equal to negative p sub k minus 1. That means the price just keeps alternating between a positive value and its negative value. So to be in the kernel, you need an alternating signal so that on the kth day, the price is c, some constant, whatever the price is, times a -1 to the k power. Again, c would be the actual price then, and the -1 is what makes it alternate. So in this scenario, the 2-day moving average is smoothing out any daily fluctuations, leaving the overall trend, which is really, in the big picture, the price is sort of stable. It just kind of flops back and forth between two prices. Now we've covered all the material for this video. I do have 3 more problems for you, but since we've covered all the material, I am going to suggest after each problem statement that you pause the video and give the problems a try yourself before you look at the solutions. The first problem defines W as a triplet, an R3, A, B, C, such that A minus 3B minus C equals 0. Show 2 different ways that W is a subspace of R3. So in other words, 2 proofs using 2 different theorems to show that W is a subspace of R3. The first way I have is this theorem here, which we had used in a previous example, and this theorem is from our video on vector spaces and subspaces. So if you have a set of vectors in a vector space, then the span of those vectors is a subspace, also a vector space. So here W, we can separate it out into 1, 0, 1a plus 0, 1, negative 3b, right? So we just look at W, we look and see which coordinates have factors of a, and this is 1 times a, this is 0 times a because there's no factors of a here, and there's 1 times a here. We do the same for b. There's no factors of b here, so that's 0, a factor of 1, a factor of negative 3 times b. So now we have W is then spanned by these 2 vectors. So W is the span of 1, 0, 1 and 0, 1, negative 3, and by this theorem here, W is a subspace. The second way we prove W is a subspace is we notice that W is the null space of this matrix A equals 1, negative 3, 1. So looking at this 1, negative 3, negative 1 times our scalars a, b, and c, or the vector a, b, c, if we multiply this out, multiply this row times this column, we get a minus 3b minus c equals 0. So again, it's the null space. W then is the null space of this matrix A. Our next question is, suppose that these 2 matrix equations are both consistent. The first one being a times x equals v. So in other words, we can find an x such that ax is equal to v, and also the vector equation ax equals w. In other words, we can find an x such that ax equals w. Both of these have solutions. We can find an x to satisfy both of these equations. So what can you say about ax equals v plus w? So if ax equals v is consistent, that means v can be written as a linear combination of the column vectors of A. So I have a1, the first column vector, times some constant x1 plus a2 times x2 up to an times xn. The same can be true of w. If ax equals w is consistent, then w is written as a linear combination of the column vectors of A. And I chose y1, y2 up to yn to be my constants now. So when I add v plus w, just adding, term by term, I have my vector a1 times x1 plus y1, my vector a2 times x2 plus y2, and my vector an times the scalars xn plus yn. Now these are just scalars in front of my column vectors of A, which means that v plus w can be written as a linear combination of the column vectors of A, which means ax equals v plus w is consistent. The last problem, let A be an n by n matrix. So if the column space of A is equal to the null space of A, show that the null space of A squared is equal to Rn. This is a sort of strange way of approaching this proof or explaining this proof, but what I really want, I'm going to aim to get Ax equals 0. In other words, Ax itself is in the null space. Then from there, it's easy. I could just multiply both sides of the equation by A, so I get A times Ax equals 0. And then I can regroup this because matrix multiplication is associative. I can do A squared x is equal to 0. And then I'm going to say that x is actually from Rn, which means all my vectors in Rn is equal to the null space of A squared. So now I'm going to fill in everything that's going to allow me to get to here. But my goal then is to say something about Ax equals 0. I'm going to start with letting x be an arbitrary representative element of Rn. So it's not a special vector, it's just an arbitrarily chosen vector in Rn. Now I'm going to consider the vector A times x. You know, you multiply the matrix A times x, you get another vector. So let's consider this vector Ax. Now we know this matrix equation Ax can be written as a vector equation, and the vector equation we get is a1x1 plus a2x2 plus anxn, where the x1, x2, and xn up to xn are scalar multiples, and the a1, a2 up to an, those are the column vectors of A. So once we have Ax written this way as a linear combination of the column vectors of A, then we know that this vector Ax is in the column space. Again, because Ax can be written as a linear combination of the column vectors of A. Now, because we're given the column space is equal to the null space, that means Ax, if it's in the column space, it must also be in the null space. So then we have that Ax is equal to 0, and so we're exactly where we want it to be. So Ax now is equal to 0. We can multiply both sides of the equation by A, and we get A times Ax equals, well, A times 0 is 0. And now, because these are three matrices, you know, even this vector, it's, you know, a one-dimensional matrice, because matrix multiplication is associative, we're going to do the A squared, the A times A first. So A squared times x is equal to 0. That means for any vector x in Rn, A squared times x is equal to 0, which means the null space of A squared is equal to the entirety of Rn. To review what we have discussed in this video, we started by talking about the null space of an m by n matrix, and the definition is the null space is the set of all solutions to the homogeneous equation Ax equals 0. So in other words, it's all the vectors x in Rn such that when you multiply by A times that vector x will give you the 0 vector. So the theorem here says the null space of an m by n matrix A is a subspace of Rn. And I had mentioned it's important to understand why this is in Rn. And if we look at our equation Ax equals 0, if A is m by n, remember if you multiply, do matrix multiplication, the dimensions here have to match. So this n has to match this. And since it's a vector we're multiplying by, then the number of columns is going to be 1. So these have to match. So this x here has to have dimension n by 1, which is why it's, if we're looking for x such that Ax equals 0, then x is an element of Rn. It's also worth mentioning that this Ax equals 0, this 0 here is the resulting vector here, which is m by 1. So this 0 is the 0 vector in Rm. Continuing on, the next thing we looked at was the column space. And the column space of an m by n matrix is a set of all linear combinations of the columns of A. And another way of saying this is the column of A is equal to the span of the column vectors of A. And then we have this theorem here that the column space of an m by n matrix is a subspace of Rm. And again, it's important we know what universe we're in. So looking at this, if this is our matrix A, the matrix with column vectors -3, 1, 6, -2, -1, 2, then the span of our column vectors is negative 3, 1 times x1, 6 times negative 2, x2, negative 1, 2 times x3. So our result of our linear combination is something that's going to be in R2. And this A, it's 2 rows by 3 columns. So it's the M number that the result of our column, our linear combination, is going to end up in. So one important point, which we talk about here, is that the null space is in n-dimensional space. The column space is in m-dimensional space. So these are two different universes. We also have the row space of an m by n matrix, and that's a set of all linear combinations of the row vectors. So the row of A, we have this theorem that says the row space of A is a subspace of Rn. And then the most important contrast between null of A and column of A is the spaces they exist in. They're two different universes, and it's important you know, otherwise, if you don't even know what universe you're in, it seems like you're terribly lost. So hopefully this makes sense to you. Then the last thing we talked about were linear transformations. Because linear transformations can be represented by matrices, we have like the analogy of the null space. First, let's define the linear transformation though. So if you have a transformation T from a vector space V to W, and the transformation is essentially a rule that assigns every vector x and v a unique vector tx and w, it's linear if t of u plus v is equal to t of u plus t of v, and t of a scalar c times u is equal to the scalar c times t of u. Then once we know that the transformation is linear, and by the way you can represent it by a matrix A, then you can define the kernel, or the null space of T, and that's the set of all vectors u and v such that T of u is equal to 0. So you can see it's totally parallel to this idea of null space. And then the range of T is a set of all vectors in W of the form T of x for some x and v. And we have this theorem here that the kernel and range of T are subspaces of V. So that's it for this video. Thank you for watching.